If each resistor in the circuit shown has a resistance of 5 ohms, what is the current passing through the 3-volt battery? Okay, that's not too bad. So first, draw a picture. Bam, picture is mostly drawn. So we have 5 ohms here, 5 ohms here, and 5 ohms here. So one of the first things I do when I look at a circuit problem is I try and combine the resistors by series and parallel. So series, you add them together, and in parallel, you add the reciprocals and then take the reciprocal of that. So here we have a couple in series, and so pretty much every time I combine a resistor, I redraw the diagram. It does take some time, but I think it's worthwhile. So draw it like this, maybe another resistor over here, got a battery there, and then we have another battery here. Try and get everything connected. So then these two, when they combine, will just become a 10 ohm resistor, because resistors in series, you add their resistances. So then we have 5 volts, 8 volts, and 3 volts. And we're trying to find the current through the 3-volt resistor. 3-volt resistor, 3-volt battery. Good call. 3-volt battery. So I'm going to say that this is, I'm going to draw currents. I'm going to call this I1. Draw another current going this direction. I'll call this I2. Draw another current going this way called I3. And one of the things that you can see, which is important to notice, is that the current that goes through the 3-volt battery is going to be the same current that goes through the 10 ohm resistor, because there's only one path here. And so this current here comes down this way, and I have to go through the 3-volt battery. For this, I like to use the hydraulic analogy. Hydraulic analogy basically relates all the electrical components to basically pipes and pumps and filters, and diaphragms and water wheels, etc., etc. And it goes a little overboard, but it's pretty good for the basics and intuitive understanding. So the important point here is this current I1 goes through both the 10 ohm resistor and the 3-volt. So if we find this I1, then we'll find the answer we're looking for. There's a couple ways to approach this. The more traditional way would be using Kirchhoff's voltage laws. Kirchhoff's voltage law and Kirchhoff's current law. So you basically draw circles, like so. I try and go in the direction of that you think the current is going to go, but it doesn't have to be. And so the idea with Kirchhoff's voltage law is that in any given loop, the voltage drop at a single point will be 0. When it comes back to itself, it'll be 0. So the way you do this in practice is you draw a point. When you go through a battery, you look at the change in resistance, change in voltage. Gross conceptual change in voltage. And so for this, we'd say 3 volts, because we go through this battery, come back up through the 8-volt battery, plus 8 volts, and then we're going to have a voltage drop across the 10 ohm resistor. So V equals IR, Ohm's law, and so the voltage drop is going to be IR. So minus I1, because that's current 1, times, and I'm going to say that this is 10 ohms. And then we get back to this point here, so we say equals 0. We do the same thing with this loop that we drew over here. You might be like, well, how do I choose the loops? You can choose them however you want. You want to choose the loops, though, so they don't necessarily cancel each other out. So if you drew a loop like this, you wouldn't want to then draw another loop going backwards like that, because it would basically just be the same set of equations the whole time, and it wouldn't give you anything particularly valuable. So doing the other loop, let's say we start right there. I think I should draw that purple, just for consistency purposes. Purple. Go through the loop. We start here, go down, come up, hit the 8-volt. Now we're going through the 5-volt, but we're going backwards from the positive side to the negative side. So that's going to be a 5-volt drop. So we write that as negative 5 volts. We then come to the resistor, and this is going to be a voltage drop. And the reason we know it's a drop is because we're going through the resistor in the same direction as current. We're saying that current's going this way, down, and around. Now, we could be wrong, but we're going to assume that we're right for this portion here. If we get a negative value for the current to, then we know that we just drew it backwards. Okay, so we have these two equations, and these are Kirchhoff's voltage laws. This is the Kirchhoff's voltage law. You have a loop, and the voltage difference at any point, one with a loop and one with just being there, will be 0. That's the idea with Kirchhoff's voltage laws. We then have Kirchhoff's current laws, which basically says that at any given point, we'll say this point right here, specifically a node where multiple points come together, the current coming in will equal the current coming out. So we can say here the current coming in is I3, and then coming out is I1 plus I2. And then looking at these equations then, this is a relatively simple, these can get crazy complicated. But whenever you see kind of batteries coming together like this, or batteries in parallel, it's going to be hard to analyze the circuit, generally, through traditional reducing of resistors, followed by Ohm's law. So this is a lot of times when you run into Kirchhoff's voltage law, but these equations are actually relatively simple, and I think we can solve them for the most part, like independently. Usually you have to do some sort of linear algebra, matrix theory, which is good to know, row reduced echelon form, if you will. That's not necessary for this. So we look at this, we got 3 volts and 8 volts, that's going to be 11 volts, and we're going to move this to the other side, equals 10 ohms. I probably don't need to leave the units on there, I am. I1, so I1 equals 11 volts over 10 ohms, which equals 1.1 amps. We know, V equals IR, that's Ohm's law. So current equals voltage divided by resistance. This is voltage, that's resistance, so it makes sense that we get a current of 1.1 amps out of that. We could do the same thing if we wanted here to find I2, this one, and then if we wanted to find I3, we could use this relationship that we wrote down right here, I3 equals I1 plus I2, so we basically take I1, add to it I2, and that would give us I3. And then we can do this because we use Kirchhoff's voltage laws and Kirchhoff's current law. Kirchhoff's voltage law, again, the loop. Kirchhoff's current law, at any given node, the current going in will equal the current going out. And then at this point, it's just solving for variables. We have 3 equations, 3 unknowns. Bam, we can solve everything. That's the traditional way of approaching this problem. A slightly less traditional, more intuitive way of approaching this problem is just kind of looking at it and reasoning it out. So if we look here, I'm going to quickly scribble this, draw that straight, call this 10 ohms. I know, I should be more careful with my drawings. I'm not. So if we know we want the current through the 3 volt battery, so this one right here, well, this battery right here is maintaining a 3 volt difference across this portion right here. 3 volt. This is maintaining a 8 volt difference across this portion right here. And then they're connected right there. So we know that the difference between this point and this point will be 11 volts. And so we have a resistor. It's really 2 resistors, but we combine them into one. We have a resistor with 11 volts across it. So we use V equals IR. I equals V over R, and we have a same thing we spent all that time deriving before. Now we have 11 volts across a resistor that's 10 ohms, and we get 1.1 amps. And we know if this current's going through this resistor, it has to go through that battery as well because it has nowhere else to go. So that's a quicker, more intuitive way. Like if you have 30 seconds to solve this problem, I do it the second way. If you're given, 20, 30 minutes to solve it, use Kirchhoff's voltage laws, Kirchhoff's current laws, and be more formal about it. But if this is like a 30 seconds, 1 minute at most to solve, yeah, look at this, be like, okay, battery maintains a voltage, another battery maintains voltage, put them together. All I care about is this side of the circuit. Don't care about that side at all. Bam, take the answer and just kind of run with it. So I probably should check to see if I have the answer over here. I do, which is excellent. 1.1 amps. So that is how I would approach this problem. Hope it helps. See you next time.